Okay, so we want to talk about biasing the transistor. So what we have is we're going to put a DC voltage here, and before we had an AC voltage there. And our goal is to make it such that our output right here is halfway between the low, which is ground, and the high, which in this case is 10 volts. So we want this to sit right around 5. So what we're going to do is, first of all, let's just do this with the DC source. So we put in a pulse, and we're just going to sweep this. So you see that I just have a voltage going from 0 to 10 volts. And then this, when my voltage is small, I get 10 volts. So this is cutoff, this is saturation, and then this is our linear region in between. Let's change this to RV of B. Okay, and then we want 5 volts. So in order to get 5 volts, we need like 2.3 volts. So if I make this 2.3 volts and run it, you see we get our 5 volts. The problem is we typically don't want to have another DC voltage source. So we have one power supply here, and we want to use that one power supply to be able to run the whole thing. So that's called biasing. So let's go to Wikipedia and put in BJT biasing. Okay. So basically, we are going to look at fixed biasing, and we're going to look at voltage divider biasing. Okay, so the first thing is we have this power supply. That was our DC voltage, and they call it VCC. We called it VDC for our DC voltage. And we just want to control the current into the base, so we're basically just going to put a resistor in there. And we're trying to control our collector current. So with this simple case, here's our transistor, and then we're basically putting a resistor right here. So this was our RC, this is our V out, and this is our base resistor. And so what we see here is this is my IB. So I can come in here and say and we're just going to do a KVL loop kind of around here. So my base emitter loop. So what we have is we have VCC is equal to RB times IB plus the VBE, which we're just going to use 0.7. So we see that IB is equal to VCC minus 0.7 over RB. And then my collector current is going to be equal to beta IB, which is beta VCC minus 0.7 over RB. Okay, so in our case, we have an RC equal to 1 kilo ohm, and so we want V out to be equal to 5, which is equal to 10 minus RBIC. So we want our IC equal to 5 milliamps, okay, which is equal to 300 times 10 minus 0.7 over RB. So we solve this, and you see that we want an RB equal to about 558 kilo ohms. Okay, so let's go do this in LT Spice. So what we're going to do is we get rid of this DC source, and we're just going to wire up to this supply right here. We are going to make this a resistor that we're going to sweep. Type the letter S. And we're going to do a dot step param. We want to vary R, and we're going to go from 100K to 1000K in 10K steps. And we put that down here. And we're going to change to a DC operating point. And then we run this. We don't want that anymore. So we'll just look at our voltage here. And so you can kind of see that you're coming along here and then it sweeps up. We're looking for 5 volts. So we just move this until we get to 5 volts, and you see we're at 576. So if I make this 576K, get rid of our step. Okay. And you see I have a collector current of 5 milliamps. I have a V out of 5 volts. Everything worked great. Okay, so that is our simple voltage biasing. Okay, so now let's keep going. So you can kind of see here's the equations that we derived. Okay, so now we're going to go down to resistor divider biasing. So now in this case, instead of just having one resistor connected up to the base, I'm going to make basically, it almost looks like a voltage divider here, except for there's a tap in the middle for my base current. And so then I can take these two to control that voltage. Okay. And this is called resistor divider biasing. Okay, so now we have this. So this was our RC, this is our R1 and our R2. So you can kind of see that I'm getting a little bit of current that comes along here. Okay, and this is our VCC. So what we're going to do is we're going to come in here and do a Thevenin equivalent looking into that terminal. So we're basically breaking here and finding the Thevenin equivalent. So open circuit voltage is going to be equal to R2 over R1 plus R2 times my VCC. And then if I look at that, when I'm looking into this terminal, we short out our independent source, and the R1 and the R2 are in parallel. Okay. So now I can take and replace this part with my Thevenin equivalent. So what we have now is we have this right here. And now, again, we're looking for this base current. And so the base current is going to be, we're going to do a KVL around that loop. And so then we have minus V Thevenin plus R Thevenin times IB plus my VBE, which is 0.7. So we see that my IB is going to be equal to V Thevenin minus 0.7 over R Thevenin. And then I can plug in what we calculated. IB is going to be equal to VCC times R2 over R1 plus R2 minus 0.7 over R1 in parallel with R2. Okay, so what we see here is that we have two variables to play with. So I'm not stuck with just one value that always works. I can control the R1 and the R2 to get things to work. So I can choose them both really big or both really small, and so it gives me more control over that when we analyze all of this. Okay, so now when we go over here, let's rebuild this with our resistor divider biasing. So we're going to put one resistor here and one resistor here. And it looks like we missed that. Make sure there's a dot right here. I've seen students kind of cross it across and miss it. Okay, so here's our R1, here's our R2, and we're trying to get this. Now, we could pick one and sweep the other one, and so let's do that. So let's come down here and call this 10K, and then we're going to call this R, and then we go dot step param sweeping R 10K to in 10K steps just to get a start. And then we're going to sweep that. Look at this voltage. And so you see that it kind of goes like this. So we can zoom in a little bit on that. So this is going up to 150K. So let's go from 100K to 150K. 0.1K steps just to give us a little bit better resolution. So we're doing a lot more steps, so it's taking a little bit longer to do. Let me pause the video while. So again, we can look here, find out where 5 volts is. And then this is 108K. So we make this 108K. We don't need the step parameter anymore. And we run this, and we get a V out of 4.9. You know, and here is my collector current of my 5 milliamps. And so everything seems to work fine. This gives me more control. I did 10K and I got 106K. I could have made this higher voltage, and I would have got a higher voltage there because they're going to balance out between the two. Now, when we're adapting this, let's say that we wanted it to be a little bit higher. So this is at 5 volts, and let's say I want this to be at 6 volts instead. If I want this point to be at 6 volts, then I want less current to go in. If I want less current to go in, I want the effective voltage here to go down. So I'm going to make this a little bit bigger, call this 120K, and we run it. And you see now my voltage moved to 7. So I can control that voltage by just tweaking it because I understand what's going on. Okay. So now that we have all of this, the next problem is we want to look at stability. So when we look at the BJT, here's our 2N3904 data sheet, we see that the DC current gain, which is our beta, they call it HFE, varies anywhere. We're in the milliamp range, so it's varying from like the 70 up to maybe 300. So it has a huge variation on beta. So we're going to come in here and see right now. Let's put this back to our, what, a 107K? Is that what we had? Okay, so we're at 4.7 volts. So now what we want to do is we want to see what happens if our beta changes. So we're going to go dot step. We're having NPN. And then the 2N3904 transistor. We want to vary our BF, and we're going to go from 100 to 300 in steps of, let's just do 50 so it calculates fast. Okay. So then we run this, and what we see here is if our beta changes, you know, it's varying everywhere from 8 volts down to 4.5 volts. So from day to day and transistor to transistor, and if everything heats up, you're going to see my bias point is going to vary all over the place, and I want to be able to create it more stable. So we need to give up beta stability. And so what this is doing is they have emitter biasing. So what we see here is that they put a resistor down here in the emitter. Let's see what happens when I put that resistor down in the emitter. Okay, so this Thevenin equivalent stays the same, so let's just redraw that. But now we're going to put an emitter resistor down here. Here is our RC, and then this is our VCC, and this is our R Thevenin. Okay, so now we have an emitter resistor down here. So now we're going to redo our circuit, our loop, and so we have V Thevenin plus R Thevenin times IB plus my 0.7 plus my RE times my IE equals 0. Well, we can change my my IE into an IB by multiplying it times beta plus 1. This is an IB. Okay, so now we see that my IB is equal to V Thevenin minus 0.7 over R Thevenin plus RE times beta plus 1. Okay, and we really don't want to stabilize IB, we want to stabilize IC. So IC is equal to beta times IB, which is equal to beta V Thevenin minus 0.7 over R Thevenin plus RE times beta plus 1. So now if we come in here and say that RE times beta plus 1 is much, much greater than R Thevenin, then this becomes right? And this part here is basically 1. So now I've created it by adding in, as long as I do this constraint here, if I do that constraint there, then we end up getting a IC that's independent of beta. Okay, so we choose that, and beta tends to be pretty big, like in the hundreds, and so the RE doesn't have to be that big in order to stabilize it. Okay, so let's go through and do our beta stabilized one. Okay, so our smallest beta is 100, so we want RE times 100 to be much, much greater than R Thevenin. Okay, so R Thevenin was originally 10k kilo ohms in parallel with 100 and something kilo ohms, which is approximately 10 kilo ohms. So that means we have 10 to the 4th divided by 100, which is equal to 100. So we want our RE to be greater than 100 for this to work out. Okay, and I guess ideally we want this much, much greater than 100. So let's just go in and use RE equal to 1 kilo ohm. So we're going to come in here and add a resistor in here that's 1K. Okay, we're going to leave this one at 10K, and we're going to resweep this. Okay, to figure out to get this all biased in. We will do this again later. S.step param R we were sweeping from 100K to, let's hope it's about the same. 10K. And we want to do an operating point, so we sweep this. Oh, we didn't get, so this has to be bigger than, this has to be smaller than 100K, so because we're trying to get to 5. So we're going to come in here and make this one 100K, and we will sweep this one. And that one was around 10K. So we're going to go from 1K. Okay, let's try that. Okay. Oh, we have to keep going. Okay, so now we are looking for our 5-volt point. Oh, I guess it's near the bottom, so about 300K. So let's just put in 300K here. Now you see our Thevenin equivalent is closer to 100K, so this is going to be, should be pretty stable now. Let's check and make sure we're at the right point. So 5.07 volts. Okay, so now we're going to come back in and put in our step param, or our beta changing, NPN 2N3904. We want to change our BF from 100 to 350 ohms step, or 50 steps. And then we run this and look at our, and so now instead, before we were going from 8 down to like 4, now we're going from 6 to 5. Okay, so we're much more stable on our output by adding in this emitter resistor. So this is emitter biasing. You know, if we go and look on Wikipedia, here's the equation that we kind of derived from before, and then they make this approximation right in here. And so you see now this approximation here is independent of beta, just like we had before. And so that is called emitter degeneration, okay, which makes everything more stable. And that covers voltage biasing. And here is the basic configuration